everyone. I'm Susan Nash, and I'm at AAPG. And we have a really wonderful and unique experience today with, I think this is our first APG Academy with the topic of offshore wind, which is exciting, emerging area. And also, it's our first time to partner with the Society of Underwater Technology and the U.S. division. And I'm excited about that. The way that came about is that our president, Claudia Hackbarth, was at GeoGulf, and she happened to hear a presentation by Andy Hill, our presenter today, and she just loved it. She thought it was great. She used to work in decommissioning when she was at Shell. So at any rate, she wanted me to read a little couple of sentences because she's unable to be here today. So she wanted me to read. Claudia Hackbarth first heard Andy Hill's excellent presentation in a shortened form at the Houston Geological Society earlier this year. Immediately afterwards, she asked Andy if he would consider doing a full-length presentation for us as a webinar, and Andy graciously accepted. The subject material is both informative and inspirational for those energy geoscientists wanting to know more about alternative energy operations and opportunities. While Claudia has another AAPG-related engagement, and we'll listen to the recording later, she wanted to publicly thank Andy now for giving his time to do this for all interested AAPG members, and also to thank the Society of Underwater Technologies. So thank you. And just as a little bit of bio, Andy Hill is the Engineering Technical Authority for Marine Geohazards for BP. He has worked on projects globally and introduced or championed some of the most significant developments in geophysical site investigation. He has published widely on the subject and been a director or contributor to numerous industry documents. So thank you and welcome.
Thank you very much, Susan, for your introduction. Just a few words on SUT, the Society of Underwater Technology. It's a learned society based in the UK, but we have a branch here in the US, hence SUT-US, and we have various committees, of which one of those is the Offshore Site Investigation and Geotechnics Committee, which I'm chair in Houston, or in the US, apologies. And we recently had our 5-yearly conference in London with 600 attendees. So this presentation not only is an update of the presentation that I gave at GeoGulf back in April, but it also has borrowed heavily from some of the research that was presented only 2 weeks ago at the conference in London to bring this smack up to date, as you might say. So I'm talking about geoscience and how it's relevant to development of offshore wind facilities. So what am I trying to do today? I want to emphasize to you all, if you aren't already aware, of just the sheer scope and scale of offshore wind projects. Following on from that, to highlight the geologic settings in which these are being sited are varied and complex, and that has an immediate impact on the choice of structures and foundations for those developments. Those implications are significant, whereas for an offshore oil and gas project, foundations costs might be about 3% of total project costs. For an offshore wind project, it's greater than 45% of the total project costs. So site investigation and getting that right is front and center in terms of its relevance. And it has a significant knock-on, therefore, to project viability. If we get the incorrect site investigation, we might go for licensing of an area that is proven to be undevelopable. Or if we have inadequate site investigation, we might have significant installation or operational surprises further down the line. So this drives the need for efficient and effective subsurface processes and understanding of the various issues at play. So that's what I'm aiming to do today. And as you're all, or probably all, AAPG members, let's start in an oil field and an old onshore oil field before we head offshore. So here we are in the Yates oil field in West Texas, developed in the 1920s, and you can see the land use pattern there in terms of vertical wells, about 20 wells pads per kilometer squared. And if we compare that to an adjacent modern onshore wind farm, this is the Desert Sky wind farm, also in Iran, West Texas. It's a 160 megawatt project developed in 2001 with 107 1.5 megawatt turbines. And in this picture, there are about 65 turbine locations imaged with turbine heights of about 100 meters, foundations 4.2 meters deep. And you can see that in addition to the turbines, there's a need for gathering station, miles of road, cabling, etc., etc. So onshore wind has quite an impact in terms of land use. And while onshore oil fields have got much more efficient in their is very limited. So if we look at the UK on the left-hand side there, that's the Midhill 76 megawatt wind farm in West Scotland, just outside Stonehaven. And on the right-hand side, that's the Witch Farm oil field in Dorset in the UK, the largest onshore oil field in Western Europe, about 500 million barrels. It's also in an area of World Heritage Site and a designated area of outstanding natural beauty. Now, through the use of extended reach drilling and indeed horizontal drilling, the impact of onshore oil fields is significantly reduced in terms of its land use. But for wind, it's still pretty significant. And this is only 76 megawatts of wind, 33 towers, so only 1.5 megawatts or so per turbine. Wind needs much more increased turbine sizes, which means increased permanent visual presence, which means more concerns about what it means in terms of environmental impact onshore. And there you can see the equivalent land use impact of the Witch Farm oil field in Dorset. Same lateral scales. So what is the result of that? Going offshore becomes highly attractive, particularly if we're out of sight of land, has reduced visual impact, or if we're over the horizon, no visual impact, negligible land use. We move into national federal authority jurisdictions, which sometimes simplifies the process. At the scale of demand required to offset our coal, oil, and gas-powered electricity, the scale of these projects needs to be really large for us to be able to meet our net zero demands. So as a result of this, offshore is therefore the direction to go. And as I say, preferably out of sight of land. So what's entailed in an offshore wind project? Well, obviously we have to have the wind turbines themselves, and we have to consider the turbine foundations. It requires offshore substations for the electricity to be routed through. And in addition to that, offshore converter stations. Everything, of course, has got to be linked together by intra-array cables, and then export cables to the shore. We need to consider the cable landfalls, and then finally onshore, plugging into substations to connect to the local grid. In terms of the turbine developments, the structural concepts are probably immediately familiar to anyone that's linked to offshore oil and gas projects. To date, the monopile has been the dominant facility concept of choice, but it is very limited in terms of its water depth possibility. So 20 to 45 meters of water depth, we're really talking about gravity-based structures, monopiles or suction-based structures. We move into deeper water, we start to consider jackets, either with suction bucket foundations or piled piles. And then out beyond 75 meters of water and to greater than 600 meters now, we're pushing beyond that. We're either talking about tension leg platform type turbines or anchored arrays. For all of these, we need to obviously understand water depth, but we need to understand the foundation soils that directly impact on concept selection. And therefore, it has an impact on our survey design to be able to understand what's happening on and below the seafloor. And how deep we need to image below the seafloor is related to knowing exactly the type of concept foundations that are being considered in a particular area. So just in terms of comparative facility scale, for those of you that are familiar with Houston and the Galleria area, I put there the Williams Tower. That's 277 meters in height. The industry now, state of the art, is getting towards 22 megawatts wind turbine designs, rotor diameter of 250 meters, and total height of about 350 meters or more. Wind array sizes up to 3 gigawatts. Wind farm will therefore need to have 150 of these turbines to be able to meet the energy output. So what does that look like in reality? Well, I've just put in some of these turbines along Post Oak Boulevard in Houston. This is a view from Highway 6 and I-10. Each of those being about 277 meters in height, as I say, 5 of them at 1 mile intervals. But for an array that we're talking about, there'd be another 18 of those coming towards you in the field of view. So again, this just immediately emphasizes why going offshore is particularly attractive to get the scope and scale of the arrays that we need. And another example of just the scale of these projects, this is the Forties field in the UKCS, supergiant oil field, 4 to 5 billion barrels of oil, developed with 5 steel jackets in about 140 meters of water, and has associated pipelines. And the types of geohazard surveys that we do in those water depths are represented by that red square down in the bottom left, which is about 3 by 3 kilometers in size. So we would have done a couple of those for each of those platform sites. By contrast, this is the footprint of the Sophia 1.4 gigawatt wind farm underdeveloped currently in the UK. Project array is 593 square kilometers. It's going to need a number of, well, at least 100 turbines in that area, plus converter stations, and hundreds of kilometers of inter-array cables and export cables. And whereas for an oil field of the size of Forties, we would have done a few of these relatively small surveys. For an offshore wind farm, we actually need to survey the entire area to get a full understanding of the geologic variability from seafloor down to the foundation depth that we're interested in. So probably up to 100 meters below the seafloor. So this is a significantly larger amount of work than we've ever considered before for site investigation purposes. What do those facilities look like in reality? Well, there on the upper left is a monopile. Up to 10 meters in diameter are now being produced. This one happens to be 9.6 meters in diameter, driven into the seafloor or drilled and grouted into the seafloor. In the middle, those are suction pile jackets being floated out from Dundee in the UK recently for installation by Total Energies in 58 meters of water or 192 feet if you're foot trick. And then again, concrete gravity structures waiting to be shipped out from the beach. And you can see the number of the structures that are lined up there waiting to be installed. So the numbers of structures are immense. And another example of that is this image of Nig Bay in the northeast of Scotland. This is actually where a couple of the Forties jackets and the Magnus field jacket. You can see in the graving dock in the center background, there's an FPSO sitting, waiting to go out onto a field. And then you see all these bucket platforms lined up, waiting to be installed. If you go on to Google Earth, as I did earlier today, just to check, I went on to check the spelling of Nig. If you go and have a look at Google Earth, you'll see 38 of these structures stacked up on the quayside, waiting to go out to sea. Those are the jackets in yellow, and then you can see the towers that go on top of that on the right-hand side. So these are immense engineering projects. And then we have the global spread of interest in offshore wind. This is a non-exclusive list of projects, but from New Zealand all the way to Hawaii, or from Oregon to India, the spread of offshore interest in offshore wind is significant and growing all the time. And obviously, the geologic settings of these varies significantly. So we need to be able to understand what we're getting into. And that means we need to have an efficient and effective screening process to understand the geology that we're faced with. In the US, we have a very active offshore wind activity set. Massachusetts, Rhode Island, New York, and New Jersey are certainly in the lead. This map on the right-hand side is already well out of date. Carolinas and California have also had lease sales and awards. The Gulf of Mexico lease sale the other week was disappointing, with no bids received for areas in Texas waters off Galveston, but a bid was taken in Louisiana waters. And we have bid rounds for Oregon and Maine announced by BOEM, but awaited. The award licenses sizes are similarly large to Europe. No more are we dealing with 3 by 3 mile drilling lease blocks as we deal with in the Gulf of Mexico. The yellow area that I've highlighted there is Shell's Atlantic Shores lease, and that is 750 kilometers square, or 32 equivalent to 32 contiguous Gulf of Mexico leases. And I've also put over the top of that the hashed red line, which is the glacial maximum going through some of those leases, because that has a tremendous impact on soils variability and therefore survey requirements to be able to image these heterogeneous settings. And the problem with that is that these large areas, you could hardly get more survey vessels into the areas if you tried. So a quote from Shell Offshore Wind Manager at OTC 2022, there is a global shortage of survey vessels to meet the incredible demand that there is in the offshore wind industry. The majority of activity to date has been European in the southern North Sea. Again, a very interesting setting affected by glacial, proglacial, glacial-marine, and periglacial settings. And what is particularly interesting in this bathymetric image of the southern North Sea and the areas of the UK, Denmark, Netherlands, and Belgium is that it looks remarkably similar. Come on, what's going on here? This is paused. There we go. It looks remarkably similar to the Gulf of Maine and Cape Cod areas, with George's Bank here instead of the Dogger Bank, Cape Cod and Nantucket, which are remnant glacial moraines, much as Jutland is affected by glacial moraine activity. So we're basically dealing with very similar settings in terms of glacial, proglacial, glacial marine, and periglacial settings that have been problematic in Northwest Europe and are driving this need for very detailed site investigation. And when we look at this demand implications, this is a graph that was much used at the conference in London the other week. Going along the bottom is years, and up the y-axis is the required installed capacity in gigawatts. And obviously, we've just about got to that black dot, which is about 2022. And we're looking to get to 50 gigawatts by 2030, and that's just the UK. And then you start looking at what it means to go out to 2050, be it standalone wind or whatever it might be, the number of turbines required. These are numbers times 1,000. The number of anchors installed for floating wind capacity, the area of seabed that needs to be characterized, so up to 100,000 square kilometers of seafloor and shallow soils need to be characterized, and then the number of geotechnical tests that need to be undertaken could be up to 200,000 by 2050. So to deliver offshore wind requires development at huge scale, and it means that we need huge amounts of site investigation to match it. And that again drives the need for rapid and efficient site characterization processes to support these goals. So this is an example subsurface support process. Much as we would do for offshore exploration leasing, we see an opportunity, we start to screen it, we decide whether we want to proceed or drop towards licensing. We start undertaking prioritization of the hopper opportunities, and then we make a decision as regards whether we're going to bid, and hopefully that bid is successful, and we move on into post-license entry towards actually in developing a project. In terms of the geohazard or site investigation support, obviously, as part of the opportunity screening, we need to be able to tell management rapidly what the potential geohazard risk fundamentals in an area are and how manageable those are, making use of publicly available data, define gaps in our understanding or critical risk to the project, and output that in a standard manner that management can use to compare and contrast to other opportunities. If we decide to proceed on from that point towards high grading understanding prior to a bid, then we'll want to undertake a full baseline review or desk study, really digging into potential public or commercial sources of data. Sometimes licensing authorities, such as the Bureau of Ocean Energy Management, do acquire data and make that publicly available. Capture all those data into a GIS project, produce favorability or common risk segment maps, as we talk about in exploration, to support license area selection in terms of the most favorable areas for bidding on. Produced a list of geohazard risk sources that need to be worked on post-entry, and then immediately post-entry to be ready to go straight out to acquire geophysical and hydrographic data to be able to develop an initial geologic model, and having developed that, to move as quickly as possible on to definition by borehole and cone penetrometer test of engineering soil properties to develop into an engineering ground model that supports this turbine foundation selection and facility type choices. In terms of rapid offshore screening, this is an example process of the types of areas that are critical. Obviously, database quality is an important indicator of uncertainty. The less data that we have, the increased risk that we have of incorrect assessment of conditions. Bathymetry obviously has a direct impact on the simplicity of installation or the choice of facility types. anthropomorphic footprint in terms of past human activity, which might be paleo activity, through archaeological or even wartime and industrial activity such as oil and gas. Soils variability, a hugely significant factor in directly impacting on foundation design, assessed by likely degree of homogeneity in the soils column and the risk presence of complex soils, which I'll come to later. Rockhead presence, if it's within the foundation zone, is significant in understanding the potential type of rock that is actually present and whether or not it's going to be susceptible to piling or other types of foundations. Hydrodynamic processes, a modifying condition because it can lead to scour around facilities. And then finally, seismicity, another modifying condition as it can have impact on the structural design and also secondary impacts in terms of slope stability in deep waters. So what does that mean to the US? As I said, a focus to date has been up in the northeast of the US, but there's also been licensing of the Carolinas, Gulf of Mexico, California, and we are awaiting lease sales in Oregon and Maine. So database quality, well, the majority of the announced areas have seen negligible commercial geoscience activity since the 1980s. So that is with the exception being obviously the Gulf of Mexico. Soils variability and rockhead presence, that has an impact. Hydrodynamic processes, as we'll see in a minute, that has an impact. And seismicity, evidently we're dealing with both active on the west coast and passive margins on the east coast and the Gulf of Mexico. And we also have concerns on anthropomorphic footprint on the seafloor. So in terms of database, this is an example from the Gulf of Maine. As I said, the majority of these licensing areas have been devoid of recent commercial interest because there's been no offshore oil and gas licensing in these areas since the 1980s. In terms of the Gulf of Maine, the oil and gas activity was out on the Georges Bank and deeper, so there's very, very little or no seismic data in the area of interest, which I've just looped around there in red behind Georges Bank. In fact, there's only 2,500 kilometers of sub-bottom profile data and 55,000 square kilometers, which isn't very much. And we know that it's a highly complex glacial background, as evidenced by multiple ice advances out towards Georges Bank and retreats. So in the absence of detailed data, it requires thinking out of the box to derive understanding in absence of any database to come up with this sort of estimated risk elements that Tatum published in London just the other week. In terms of complex soils and rockhead, this is some extremely high resolution 2D seismic data. It's actually from the UKCS, but it is equivalent, and in fact, uncannily equivalent to what you'd find in the New York Bight in terms of a quaternary succession affected by multiple glacial advances and retreats or outwash effects or periglacial effects. That's highly complex and relatively thin over rockhead. And then that means that rockhead comes into the foundation zones with concerns for what is the expected rock type and acceptability for piling, as the type of piles that we might be considering going to go 50 meters or so into the seafloor, which will mean they'll be tipping into the rockhead in this particular instance. And we can see just how complex the different fills are in there in the quaternary. And in this particular area, 14 different sequences have been identified across this particular area of wind farm development, each of them having different geotechnical properties. And then I mentioned the previous one, we had Cretaceous subcrop. Well, what is the rock type? So one of the issues in the North Sea has been chalk, piling into chalk. It has had a widespread impact on European offshore wind areas of interest. That's just a map of chalk across the Northwest Europe. It's fractured, it's sensitive. Obviously, it's calcium carbonate, very soft calcium carbonate rock. It is heavily damaged by the impact of piling. Effectively, as you pile into it, the rock immediately around the pile wall becomes like soft putty in that annulus around the pile, as well as a fractured zone extending around the pile shafts. That leads to complex engineering concerns around pile design and the long-term pile integrity of the structures once they're installed. The result of that is much ongoing research, at-scale testing, such as in these sites at St. Nicholas and over in Denmark, and much concern about the relevance of design codes and the need to update them such that excessive conservatism in design isn't being applied. Then we also have issues in the Cretaceous of glauconite and calcareous sands. So on the eastern seaboard of the US, south of the glaciogenic zone I talked about earlier, there is significant variation in soils and soil properties with difficulty in classification as a result. One of the big concerns at the moment off New Jersey and slightly to the south is the presence of glauconitic sands and how they change in their properties during piling. Further south, as we go to the Carolinas or on further south, we move to the risk of calcareous sediments, which are highly contractive. They can suffer from significant reduction in strength, which means that we have the risk of pile running, i.e. excess self-penetration, if we don't understand the soils correctly and the presence of high degrees of calcareous sediments in soils. The classic worst case of this is installation of the North Rankin A platform off northwest shelf of Australia, whereas it was expected that the predicted blow count for installation of the piles for the platform would require 4,000 to 5,000 blows, whereas the actual blow count was 400 to 500 blows, meaning there was significant under support of the structure, resulting in the need for millions of dollars of remedial action to be able to provide the correct amount of support to the structure. We are already seeing similar issues in offshore wind farms in the Far East with calcareous sediments such as off Taiwan. In terms of glauconite, it needs very careful site characteristics, put my teeth back in, excuse me, site characterization. We need to understand the type of bedrock present and for the potential reworking of glauconitic particles. Early identification, therefore, during site investigation is imperative, and particularly through site, in situ sampling, which also requires very careful handling of the soil samples and specimen preparation, and then representative lab-induced degradation. And again, in a similar manner to the chalk, when you drive a pile into glauconitic sands, you see a breakup in the glauconitic sand particles. The image there on the upper left is a photo of a sample taken alongside a pile driven into glauconitic sand. The greenish hue is the altered sediment up to half a times pile thickness distance away from the pile. And the yellow is the undisturbed natural in situ glauconite particles. So what is happening here is we're seeing basically the native particle size distribution being radically altered through crushing. And as a result, that can result in significant changes in shaft friction during driving of the pile. It can result in premature pile installation refusal, and therefore resulting in enduring degraded long-term pile response. So understanding the presence of these soils is important. Going further south on the eastern seaboard, we have calcareous soils, very similar to what we're seeing in the terms of the variability offshore Australia versus the nearshore to the deeper water. On the left-hand side, these are samples taken ledge point, nearshore, browse, offshore, and you can see the level of calcium carbonate within the soils that were being sampled, up 70% up to 90% of the soil. And similar samples taken on the east coast, for example, as the micro photo of Blake Plateau sands, seeing that we're seeing maybe not as high percentages as we're seeing in Western Australia, but still significant, that needs to be understood. And what we need to take into account in terms of understanding just what is going on is to actually apply carbonate depositional system analysis in terms of understanding whether we're dealing with pelagic sediments or coastal bioclastic sediments, and what that might actually mean to us in terms of the type of sediment particles that we're going to actually see in these different arenas. So you might not think that carbonate depositional systems has an impact on offshore wind development, but it certainly does. In terms of seismicity, ISO has a set of standards for seismic design procedures, an association scheme for earthquake design, and these are published in ISO 199012. And they zone the world's seaboards on the basis of spectral accelerations, horizontal spectral accelerations. And what we see, not surprisingly, is the US Atlantic margin and the Gulf of Mexico sit at the lower zones, zones 0 to 1, therefore a passive margin, whereas California and Oregon, quite the opposite, zones 3 to 4, an active margin, with parts of Oregon and Washington being up to 0.5 1 second oscillator periods, are very high indeed in terms of what we expect. And that has an impact into what we need to be thinking about in terms of California. This is Morro Bay. You can see a little insert map down in the bottom there with lease sales. These are data acquired by USGS for BOEM to release to help inform people of what's going on in these areas. The water depth is quite significant, 600 meters plus. So this is a floating wind setting, the first lower 48 offshore area to have floating wind as its main development case. Projects therefore need to consider the anchor types that they're going to need to secure these. Therefore, that has an impact on soil types. And soil types also has a risk, needs to be understood because of the risk of slope instability, particularly as we're in this active margin setting. So the data that we see here, published by BOEM, we see various types of silts and claystones in the upper section. We again see basement rock presence within the relevant foundation zone, and that impacts on potential use of suction bucket anchor types for floating wind opportunities. And as I say, with the active margin, we need that to be directly incorporated into design of the anchoring and then into detailed slope stability risk modeling over the life of the array. Anthropomorphic footprint, an example of the issues that we face there are unexploded ordnance or disposed of munitions. Pretty interesting case here in the southern North Sea just a few years back, where a fishing vessel was completely and utterly blown clear of the water as it was recovering its pots, with significant injury to the crew. Almost certainly this was old World War II munitions that hadn't been previously identified on the seafloor. We have munitions issues in various areas that we have in play up in New England or offshore New England. And in addition to that, we have the issues of marine archaeological effects from now submerged original native grounds and concerns from native tribes in the New England as regards what might be being done to their ancestral grounds. And then finally, hydrodynamic processes, the scour. Already scour issues are being experienced in New York bight projects, but scour around monopiles or jacket foundations is a significant risk to long-term operability. The early European wind farms experienced this quite significantly, and on the right there is the example of the UK Scroby Sands directly offshore Great Yarmouth, and you can probably see in the photo, you can see the tide running past some of those turbines in the background. And the impact on that was that post-installation scour pits developed around the individual piles far faster than had been previously anticipated, with impact not only on the piles themselves, but also on the connections of the inter-array cables, which you can see in the bottom there. So this results in increased attention to need in design, understanding of these processes, inputs of selection of protection systems, and the need for continuous modeling and time-lapse surveys to ensure that predictions are being kept. So all these things we can assess and prioritize in terms of what is going to be most significant to our projects. So in this particular instance, I've just put in an area that we had screened, and one of the most significant impacts in this particular area was rockhead presence. The greatest uncertainty that we had as regards whether the rockhead below a thin quaternary cover was tertiary or potentially Precambrian, which would have a really significant impact on the potential for being able to use piled jackets versus gravity-based jackets. So by doing this process, we can highlight very simply what needs to be addressed most actively post-entry into a particular area. So the hazards that we require to understand, we need to understand whether we have active seabed forms on the seafloor. We need to understand the variability in soils across an area by use of soils province mapping process. We need to be looking for the presence of unexploded ordnance on the seafloor, or whether those are UXO or in fact individual dropstones, stroke boulders. And we need to understand boulders in subsurface. Then we've got to worry about these special soils such as volcanitic or calcareous soils, scour effects, and then boulders, as I say, in the subsurface. In terms of boulder detection, it's been a concern of ours in terms of installation of conductors for oil and gas in high latitudes for decades. But now we have the risk to wind installation from either driving failure if we're driving in a monopile, issues with drilling and grouting deflection, tow damage to a monopile, or just simply failing to get the pile to the required depth. There imaged, you can see a 42-inch hole opener with actually a boulder stuck in it. Very, very rare that we actually managed to get a boulder back to as evidence to the drillers to tell them that, you know, we did tell you that there's a likelihood of boulders. But in this case, we did. But what's a 42-inch hole opener to offshore wind when you're dealing with a monopile installation that could be 9.6 meters or 10 meters in diameter, or a need to use this type of bit to drill and grout a conductor into the ground. So the scope and scale of these things are much, much larger And we really need to consider what could be down there. And in the New England case, this happens to be one of the largest glacial erratics that is left on the surface out on Cape Cod. So these glacial erratics can be really, really large in comparison to the diameter of monopile. So we need to be able to identify them in the subsurface. Immediately post-entry, we need to get right after covering our area of interest. In this particular area here, 890 square kilometers was imaged very soon after the license was accepted. We need to get understanding of variation in ground right across the whole area to 100 meters below mudline and a vertical target resolution of less than 1 meter. Typically, we might start off with line spacing 200 meters, 300 meters, but water depth, depending on, let me just get this out of the way. Depending on multi-beam echo sounder and side scan sonar, we might need to actually acquire these data at closer spacings. So to be able to get our larger survey vessels, which are difficult to get hold of in the first place, we've started making use of autonomous surface vehicles to be able to acquire these data at closer line spacings much more efficiently. We're using a variety of extremely high resolution seismic sources, sparkers, boomers, and small air guns, and streamers with group intervals of 1 meter, which are much, much smaller than we might be used to in exploration seismic. And the tow depth similarly is very shallow, which again has an impact on weather acceptability. The data that we are dealing with, down there in the bottom left-hand corner, that's your reservoir 3D resolution out to maybe 100 hertz, 150 hertz if you're really, really lucky on shallow reservoir imaging. But we're dealing with imaging out to 15, 20 kilohertz in terms of sub-bottom profilers, side scan sonars out to 100 kilohertz out to 750 kilohertz, and video cameras for correlation of what we're seeing on the seafloor for environmental assessment. So a very, very different set of equipment to what you might be familiar with from exploration. In terms of vessel availability, I mentioned about trying to get some of these data acquired by unmanned surface vehicles. This happens to be one such vehicle out acquiring multi-beam echo sounder data in the southern North Sea. That's just one shape. There are innumerable different types of unmanned surface vehicles controlled from an onshore base. It's great in terms of removing people from the field, but it also means we get some flexibility in what we're actually acquiring. And the data on the right-hand side, you've got multi-beam echo sounder data of sound waves and mega ripples and outcrop rock on the bottom there, either in terms of relief on the left or side scan sonar image on the right. In terms of penetration, we can use single channel chirp type profiler data for imaging of glacial or proglacial outwash fan deposits, but these type of sources only penetrate pretty shallow. So this is 8 meters in terms of its penetration, maybe out to 15 meters in places. So that means we really need to be thinking of something with a bigger bang behind it. And the result of that is we go to multi-channel broadband sparker imagery that gets us much deeper into the seabed, below the seabed, at still very, very high resolution. This is an example from Indonesia of tidal deposits. Typical survey program, year one will go for multi-beam echo sounder data and regional blanket seismic survey, together with environmental baseline sampling. Year two, we'll be looking to calibrate our ground model with deep geotechnical sampling, either by borehole or cone penetrometer test. And then By year 4, we'll be looking to micrositing of turbines through 3D, extremely high resolution 3D seismic survey, for example, for boulder detection and avoidance. And year 5 into detailed geotechnical program for individual foundation design. But the whole time there is pressure in terms of compacting that. So we need to make that as efficient as possible. The reason being that we pay our license fees for the area until we're producing electricity. So obviously, to make the projects as efficient as possible, we need them built and delivering electricity as quickly as possible. Oops. That means we need to rapidly and effectively come up with a soils province model or an initial geologic model, understanding depositional understanding across our area. And what we use for this is the soils province model that groups laterally and vertical variability in soils across an area to the full depth of potential foundation zone. It assists understanding and visualization of depositional settings and informs us, therefore, on the potential for degree of lateral variability in soils quality, ahead of calibration of the individual soils unit by boreholes or CPTs. In this particular instance, the colors each represent a particular soils province, and we can see that there is a change through the middle, and that is directly related to the depositional setting. On the left of the area, we're really looking at a proglacial outwash plain and fans with braided streams coming across the area, whereas on the right of the area, we're looking at depositional systems that are more related to ice-dammed lakes and lacustrine deposits. So once we have that model, we look towards initial geotechnical sampling. So we acquire soils to transform our soils model or geologic model to a calibrated engineering soils model that allows us to define foundation type across the area, installation risks, and input to project economics. And when I say installation risks, it may be a different sector, but we have the same risk of punch through that we do in oil and gas for jack-up installation barges. This is a very sad event in 2021, where 4 people were drowned as a result of a punch through of this particular lift barge. Variable leg penetration punch through, therefore, is a significant risk. And whereas in oil and gas, we might be dealing with 1 or 2 locations where we need to jack up on, when we have to do this at greater than 150 locations, we're really rolling the dice. So we really need very, very good understanding of potential for lateral variability in soils away from our structure location. That means we need to undertake microsightings of the turbines. And the layout of the array is primarily driven by the likely interaction of wind flow through the array relative to the size of the adjacent turbines. And this is really well shown in this picture of a foggy day in the North Sea, where we can see the effect of wind turbulence coming past individual turbines relative to one another. So thus, after geology inputs, the choice of structure and the foundation types, micrositing of individual turbines relative to the ground conditions becomes key as the designers of the array actually lay out spacing that they require the project to be delivered at. What could we miss in terms of micrositing? So on EHR 2D, I said we are acquiring 200 by 300 meter line spacing. 300 by 900 meters was the norm in the Gulf of Mexico for site clearance, and no one seemed particularly bothered about locating a well off a 2D line. Yet, having diligently covered 900 square kilometers data on our 2 by 300 meter line spacing, what could we really miss? And so do we really need to worry about what could be in between? Well, this is the sort of thing that could actually fit in between, and I haven't fudged this. Honestly, this is the NRG Stadium, home of the Houston Texans in Houston, and that fits very neatly in between 2 by 300 meter line spacing. So we miss something of that particular scope and scale. So in terms of turbine micrositing needs, we have our soils province model. We understand where we might have bedrock, gravelly sand, over consolidated clay. And in this particular case, we're looking at installing suction bucket jackets. Glacial dominated areas of soils and bedrock, well, they're not particularly positive, so we can rule those out in terms of over consolidated clays, not particularly positive. Some of these areas are acceptable, or these locations are acceptable, but one of them, it would look more beneficial if we could just move off slightly from where we have our line coverage. So foundations should ideally be on seismic lines. So what do? Well, preferably we have 3D data coverage at the resolution that we acquire. The problem with that is the scope and scale of what we actually need to. So I've taken, for example, an illustrative turbine layout. This would require a 160 square mile survey, so equivalent to about 18 Gulf of Mexico lease blocks. And then I put underneath that the soils province model that I showed you earlier. So in this particular case, 66% of the turbine locations lie close to or on a soils province boundary. So 3D data would really be advantageous to us in terms of understanding soil stratigraphy, identifying possible boulders and shallow gas, for example. And we want to be able to image boulders down to around 1 meter in size and be able to perfectly tie our geotechnical boreholes and wind farm foundations to penetrate to 20 to 80 meters, depending on type. That means that we have a real issue in terms of the frequency and bin size requirements of the data that we need to image down to and image around a potential turbine location to give us some slop in terms of being able to move plus or minus 50 meters to the original design location for micrositing. So what does that mean in terms of the resolution of the data? Well, this happens to be some 3D mid-resolution data acquired for a CCUS project. It's quite nice data, 9 streamers, 4-source solution. But what we're actually trying to acquire for offshore wind requires an array much, much smaller. That red box on there is the size of the array that we're actually talking about for 3D extremely high resolution data. So 10 meter streamer separation and streamers that are only about 100 meters in length. And we're imaging not down to 1,000 meters, but we're really looking to get very high resolution data to 50 meters below the mud line. To do that across an entire area is extremely inefficient. So we're looking for clever ways in which we can get the coverage that we need without actually getting complete cover everywhere. And the approach to that is to actually acquire corridors. So you actually steam your streamer array through the area, through your potential turbine locations, and build that out to the width of cover that we actually require. And in this particular case, we were looking to image bin sizes of 0.75 by 1 meter in size, instead of what you might be expecting in exploration seismic of 25 by 25 meters, or if you're lucky, 12.5 by 12.5 meters, and build that out such that we have a perfectly imaged area of 100 meters by 100 meters around our potential turbine location. And when I said we needed to be able to identify boulders in the subsurface just to show that it's possible, here you go. Here are point reflections in the subsurface in very small detail. So it can be done. Beyond that, making the most use of our data, we really need to be looking towards the benefits of seismic inversion to understand soil properties away from our boreholes or our cone penetrometer tests. So this is some of the inversion work that Vardy is undertaking quite successfully in terms of understanding what's happening away from the borehole and actually be able to come up with synthetic CPTs. So on the right of there, you can see in red is the estimated CPT trace from the seismic data, and in black underneath it is the CPT that they actually got when they did the test at this particular location. This has been talked about for many, many years and is only now coming into fruition because the quality of the data is good enough to do it. And then we need to be using rapid interpretation, automation, and AI to be able to understand the best of these data as fast as possible. So in the example on the mid-right there, we had automatic boulder and scour picking on this extremely high resolution 3D data. So that's boulders at the top and glacial scours at the bottom. And then we need to be making use of interpretation systems such as Blueware, Paleoscan, and many others to be able to rapidly develop our geologic model before going out to acquire focused geotechnical sampling to be able to come up with an engineering ground model to define our turbine layout. So in conclusion, hopefully I've shown to you the scope and scale of offshore wind opportunities requires really efficient and effective subsurface screening, both pre-license entry and upon entry. It needs to be done in a standardized manner to allow consistent comparison of license opportunities. We need very aggressive project timelines to deliver fast and efficient ground model development over very large areas immediately post-entry. We need to be using integrated use of multispectral seismic data from 20 kilohertz down to 50 hertz to be able to deliver a critical role in the design and development of offshore wind projects. There are opportunities to use 3D seismic platforms, but those designs must be cost efficient and effective and deliver the required resolution. And the volumes of data that we're acquiring, we need to use automation and AI and interpretation to be able to speed up results. However, the pace of these projects is placing a huge demand on offshore resources to acquire the data, but also on the need for qualified personnel to be able to, for example, sense check that the automation and AI interpretation is actually coming up with the results that we need. Survey vessels are in short supply, which is encouraging us to use autonomous surface vehicle survey solutions. There is a shortage of personnel, and therefore that has an impact on survey safety implications where people are actually in the field. And seismic interpretation and analysis skills, well, they're going to be in great demand in this space over the next decade. And actually, to be perfectly honest, as evidence from the graphs I showed you, for the next few decades. So be it operators or contractors, there is a huge demand to encourage graduate entry into geohazards and site investigation for offshore wind farm development. Some references there for those that are interested, a lot of those from the conference the other week, and I'll leave it there with questions, but just one thing to highlight. If you are interested in this further, there is SUT are offering an integrated offshore wind webinar, Geoscience and Engineering Challenges for Floating Offshore Wind. There'll be 5 speakers. It'll be 2.5 hours, if I get that math right. Yes, 2.5 hours in length with a panel session at the end, and you can register through that QR code. And at that, I will now leave it to questions.
Great. Well, it looks like we do have some questions, and I've gotten some emails saying that some people were like disconnected or kicked off or something. So I'm glad that we're recording it because everything was smooth on my side. But anyway, just a reminder that we are recording, and you'll get a copy of a link to the recording in an email. Okay, so Giorgio Giuliani says, can you please comment on synthetic soil profiles for ground model generation and micrositing purposes? Thank you.
So can you comment on synthetic soil profiles for ground model generation microsite? Yep. Well, this is something, Giorgio, that is really being developed and again was being talked of in London the other week. Probably the best examples that we're seeing at the moment are those being developed through inversion by Sands Geophysics in the UK. NGI are developing processes for coming up with a 3D synthetic soil model for ground model generation and micrositing. But I think the key is going to be getting this really extremely high resolution 3D data around potential turbine locations that allows us to be able to use these tools to analyze the potential variability in soils away from an individual borehole. Hopefully that answers your question.
Okay, so we have a question. Can you comment on the effect on whale migrations and referencing the Northeast US?
Okay, yes. So solution science being collected and issues on whale migration. Important thing. All these surveys that are being undertaken will have marine mammal observers on board, and they go through very careful not only looking for the presence of marine mammals, but also extremely careful in the way they start surveys. They won't start surveys if they have identified a whale in the general area. They will listen for them as well in terms of passive listening systems. So it is an issue. It is being carefully managed, and it's not just an issue in the northeast of the US, but it's an issue in numerous areas around the world. Thankfully, we're seeing more whales than we ever expected to see. It's because the whale populations must be rebounding.
Okay, so you mentioned anthropomorphic remnants, but didn't really go into it beyond unexplored ordinances. Well, you did also talk about indigenous cultures. Anyway, can you expand on that? And does SUT offer any training people can attend?
Yeah, good question. I mean, when I said anthropomorphic, it's marine archaeology, not just recent remnants of industrial development or oil and gas development, but also marine archaeology. And SUT have and do offer a 2-day training course on marine archaeology that they look into the different types of data and analyses that need to be undertaken, and I thoroughly recommend that course. I'm not quite sure when we're going to be offering it next, but just keep an eye out for the SUT-US website, and it will be coming along soon.
And I'd like to mention too that AAPG has offshore training, and well, we will have, well, it's probably not going to Madrid, but in our international conference in Madrid, there's an emphasis on offshore wind. And I just wanted to mention too, the OTC in May, that it was incredibly well attended, and there was a lot of participation in terms of different projects for offshore wind. Okay, so you answer the training. Okay, with all the seafloor geological and geophysical factors influencing piling and platform stability, can you please comment on current technologies used for monitoring platform subsidence or other instabilities?
Yeah, well, what's actually being used? Well, you can have obviously satellite monitoring systems installed on these platforms. In the past, of course, we'd do accurate surveys of production platforms in oil and gas, or make use of an array of GPS sensors to be able to monitor the long-term stability of a platform or movements thereof. The same can be applied to offshore wind facilities. There is also talk about putting sensors into piles to understand what's going on in terms of long-term stability and pile response. And as I say, again, if I showed you the program from London just the other week, the vast majority of the papers given at the conference were about pile design or foundation design and integrity and monitoring thereof. So this is really something that's there's a lot of focus on in terms of long-term integrity of these features.
It's interesting because I used to work for Kerr-McGee, and one of their North Sea fields, Beatrice, there was a wind farm near it, and it was actually retired and decommissioned, and then a larger one was installed. And then I put a link to the wind energy roadmap for Azerbaijan, the Caspian. That's pretty interesting, and I think that would be highly interesting. BP used to have a lot of operations there, but I just wonder, like with all the mud volcanoes, it's going to be quite an intriguing challenge. Of course, they have offshore platforms too. So, at any rate,
Azerbaijan is a country very dear to my heart, and in fact, I was there the week before last. So,
nice.
Yes, I know that they are looking at offshore wind. So I'll read that one with great interest. Thank you.
Oh, you're welcome. I put a link there. It's really good, and I spent a lot of time in Azerbaijan. I liked it. Okay.
I see another question about for geoscience grad students looking for internships or full-time positions. What companies are currently hiring? Well, there's a lot of survey companies that are active in this space, the likes of Fugro, Alpine, TDI Brooks, Exodus, GEMS, Geosyntec. Well, Geosyntec now bought GEMS, Benthic, and many others. So if you're interested in this area, then certainly I'd go to those. If you go to the, let me think about this. If you go to the OSIG conference website and look at the companies that sponsored the conference, of which there are about 20 or 30 of those, that'll give you a really good idea as regards who's active in this area, particularly in offshore wind, and where to go. So yes, be it from the operators developing these wind farms or the survey companies that are actually supporting the developments.
Well, this is really great. I just want to thank you again, and just also for this serendipitous occasion that Claudia happened to listen to your talk, and then she told me it was right before OTC. Oh, okay. So please comment. Please comment on using existing oil and gas platforms and integrating them into wind energy areas rather than decommissioning.
Yeah, thank you, Maggie, for your question. Good question. I believe some of the platforms, or one or two platforms in the northeast of Scotland, if my memory serves me, it was the Beatrice field, have been recommissioned with wind turbines on them. I think I'm right in that. The issue really is you could probably put a turbine on top of it, but it's the sheer volume of structures that are needed makes just one or two oil and gas platforms seem rather insignificant compared to putting in one of these arrays with a 3 gigawatt capacity. So yeah, it can be done. In the opposite direction, there are wind arrays, offshore wind arrays being put in, such as a floating wind array in the northern North Sea in Norway, that's actually providing electricity to a series of platforms to power them and to stop them from having to burn diesel or gas for power generation to reduce the footprint of the oil and gas development. So it's a bit of a two-way street, but yes, we could put turbines on top of some of these structures that have been decommissioned, as long as the jacket's still in place, that is. But actually, just the sheer scale of the electricity demand means that we need to have hundreds of structures rather than a few.
Yeah, I think it seems like it's good that there's some of the infrastructures there, like not the platforms, but just the other infrastructure. But I've always heard that there's also a huge problem with vibration on some of the platforms, which kind of made to try to convert it into and they're pretty bulky compared to the small. I mean, I really like what you're saying. The array is super interesting. But the idea of complementary installations is a nice idea.
Yeah, I see Gladys Perez in Bogota. Hi, Gladys. Hope you're well down there. Yes, offshore Colombia. Well, what that is. No. Right. Okay, that's over. So yes, I am aware that Colombia is soon going to have an offshore wind license round. And so, yeah, looking forward to seeing how that goes. Again, very interesting area from a geohazard standpoint for some of the data that I've seen there in the past. And I know that other areas in Latin America, Brazil, Uruguay, for example, are also keenly looking towards offshore wind. So hopefully for you, it'd be Bogota that gets there first. Good luck with it.
Well, just a reminder that everybody will be getting an email with a link to the recording. And just if you are an SUT member, please renew. If you're an AAPG member, please renew. If you're a DPA member, welcome. And just super exciting. And I'm just really excited to see how we're being agile and responding to new needs and using the information in the scientific background for different applications. Andy, the presentation was amazing, just totally amazing.
Yeah. I see Rania has asked the question, will SUT-US be offering any site characterization short courses in the near future? And the answer to that is yes, hopefully before the end of the year, we'll be doing a one-day course focused on the geoscience aspects of site investigation for offshore wind, which will obviously takes some of the themes that I've spoken about and expand dramatically. And then we'll follow that up with a one-day course on geotechnical engineering aspects of site investigation for offshore wind. So that'll be that piece of taking a geologic model into an engineering ground model.
Okay, so I guess we probably should go. Let's see if we have any. And it's really great to know that there's a need for training and also a demand for it. So that's really fantastic. And thank you again, Andy. And thank you, SUT, for partnering. And also special shout out to Tulsa Geological Society and also the DPA, Division of Professional Affairs. But again, I put a link to the SUT's website. So I suspect that training will be listed there. So thank you, Andy.
Well, thank you very much, everyone. Hope you enjoyed it, and look forward to seeing you at future SUT events. I think, yeah, it's the first Thursday of the month, so there'll be a networking event somewhere in Houston on Thursday. Find the location by going to the SUT-US website, and I will be there.
Great. Well, thank you, everyone. I'm going to stop recording. And if anybody wanted to review anything, I would just encourage them to look at the recording and stop, freeze the frame.